Okay, so thin-walled pressure vessels. Fairly important, keeping stuff in. So we tend to make the assumption that when we're using a thin-walled pressure vessel, stress state isn't varying through the thickness of the shell of the vessel. So this makes our calculations very, very, very simple compared to what we need to do for thick-walled pressure vessels. Generally speaking, we need at least a 10-to-1 ratio of the radius of the pressure vessel to the thickness of the shell of the pressure vessel. But if we do that, then we're worried about basically kind of two different stresses that arise. So we've got hoop stress. So hoop stress is basically kind of what would we get if we cut along the, cut the thing in half along the length. Then we get stress acting on this face here, this face here. So it's called hoop stress because the actual stress, it's oriented all the way around. So we get this if we cut there. We'd also get it like if we had to cut there, it'd just be oriented this way and this way. So again, the force is just a function of the fact that we need the force of the stress acting on that cross section to be equal to the force exerted by the pressure. So if we just look at the areas here, we've got this projected area here, and the pressure is pushing against it, and that needs to be resisted by the stress in those areas. So you'll see that since the projected area here is so much larger than the area of the shell there, that the stress level induced along that orientation needs to be quite a bit larger than the pressure that's actually being contained. So that'll be our pressure times the radius over the thickness. So we're talking, again, if we're making that thin wall assumption, we're talking at least a 10-to-1 ratio of the pressure to the of the stress induced in the material to the pressure that's being contained within. That's for the hoop stress. That's in that direction. If we're looking at the longitudinal stress, then this is our stress that is acting along the length of the pressure vessel. So, and again, the force exerted needs to be equal to the force by that stress needs to be equal to the force exerted by the pressure. So again, this projected area times its force needs to be resisted by the projected area, that is the circumference times the thickness. So we end up getting PR over 2T. So our hoop stress is going to be worse than our than our longitudinal stress as a result. So if we were looking kind of just at a little section here, then we would end up with some sort of tensile stress here, some sort of tensile stress here, and tensile stress here, and tensile stress here, and the magnitude of this would be twice the magnitude of that. Now again, we're assuming it's not varying through the thickness, and that also has the result of basically, if we were looking at technically speaking, if we're looking at, say, a cubic element that is on the inside of the pressure vessel, say the bottom here is the inside, there's also going to be the pressure pushing like the pressure is going to be pushing on it upwards. So there's going to be, there's actually going to be a bit of compressive stress there that, it's going to be equal in magnitude to that p-value. And then, of course, again, we're going to get, our longitudinal stress. We're going to get our hoop stress. And then if we look at the same cubic element, same spot, but it's on the outside. Again, longitudinal and hoop, big, and then 0 here and here. So technically speaking, there is some variation that goes on there, because that compressive needs to drop from 0. It needs to drop from some negative, some compressive amount to 0 as we vary. But the actual interactions of that tend to be fairly complex, and we're essentially what we're doing when we make the assumption that it's not varying at all. We're just going to say that is 0 throughout, and we're not. That's not all that terrible of an approximation, because the magnitudes are so much smaller. Because essentially it's varying from p to 0 in a structure where, the hoop stress is at least 10p. The longitudinal stress is at least 5p, and typically speaking, that 10-to-1 ratio is usually exceeded. So the actual impact of the compressive portion there on whether or not this thing's going to fail is relatively minor, and to a large degree we can kind of just ignore it, especially considering pressure vessels have a tendency to have relatively large safety factors applied to them. So we're not, the aim of simplifying our calculation is reasonable enough that we can just go ahead and make that approximation and say it'll be good enough once we apply the safety factor. One thing I do expect you to be able to do is use the cylindrical coordinate system when you're doing something like this. So again, most of these are going to be cylinders. You're going to be using some sort of radial measurement, so from like a radial distance from the axis outwards. You're going to be using an angle measurement, kind of taken from some predefined point, or axis, I suppose, and a height measurement. So the height measurement, that's fairly simple. Well, if we need to transform back and forth, we can use these equations. The beauty of the cylindrical coordinate systems is that essentially we can often describe, if we describe our stress state in terms of our theta in z, then that means that would be valid, and we don't need to do any transformations to that to account for the orientation if we pick a spot here, or here, or here, or here on the surface, or in that cylinder. We don't need to kind of adjust what our X stress is and our Y stress compared to our Z stress, and so on and so forth, as a result of that. It's just, it's just the stress in the R direction, or in the theta direction, or in the Z direction. Particularly in instances, if we're talking the thin-walled pressure vessels, the stresses that would be arising, which we previously called theta, sigma 1s and sigma 2s. So sigma 1 here was defined as our hoop stress. So that would be in the theta direction. So that'd be our theta stress. Sigma 2, our longitudinal stress along the length, that's our Z. And then our radial stress, again, we're assuming it's 0 throughout. Like I said, it's not actually 0 throughout. It's dropping from, as we go through the thickness of the thing, it's dropping from negative p to 0, but calling it 0 is close enough. So we can do these transformations if you really need to, but it's best just avoid it by kind of working in the cylindrical coordinate system to begin with. So we'll do some examples on the thin-walled tanks. We'll do a couple, and then we'll start getting into essentially what happens when we combine different loads to our thin-walled tanks. So in combined stress section later, will be the bulk of how we're looking at this.